All right, class part 3 of Einstein's special relativity. So far, we looked at some of the underlying postulates, and we looked at time dilation. The next section is going to continue looking at time dilation and relate it to some of the other findings that Einstein had from his special theory of special relativity. So on page 268, at the top, they talk about some experimental evidence for time dilation. There are some particles that are created in the atmosphere that only have a very, very short life. So they're going to be traveling towards Earth, but they don't live for very long. And as a matter of fact, when you do the calculations, you find that they should not live long enough to reach Earth. And yet the detectors on the Earth have detected collisions from those particles, muons. So why does that happen? It happens because the muons move really, really, really fast. Fast enough that time dilation would say that they don't just live for a short period of time, they're going to live for slightly longer. And it's that slightly extended lifetime that allows them to stay alive long enough to reach the Earth. So we actually have experimental evidence of Einstein's theory in action. So, I mean, theories are always nice, but it's nice to be able to collect some data that supports it. Theories are never proven, but they can be supported. And then it goes on to continue about a thought experiment. If you took off for 5 years and you're going really, really, really fast, you only left for 5 years, you're going to come back 5 years older. But if you left for 5 years going really, really fast, then your 6-year-old daughter will have aged by 36 years. That's the effect of the time dilation going close to the speed of light over the course of your 5-year journey. They talk about that sometimes in videos as the twin paradox. You know, two twins born exactly the same time, one leaves, comes back, and the other twin has died. Again, that's because of time dilation. What we're really going to focus on is another formula on page 269. At the bottom, it looks fairly familiar. It's the same kind of factor as we found in time dilation, but because it's on the numerator rather than the denominator, then we're actually going to get a shortening rather than a lengthening, right? When we have a small number in the denominator, a fractional number in the denominator, ends up making the result bigger. Right? Dividing by half makes it bigger. Divided by a third makes it bigger. But in this case, we're using that same factor, but now we're multiplying it. So we multiply by half or a third, it's going to get smaller. And this has to do with the length of an object or perceived length of object from an outside observer. So we find that time expands almost infinitely the closer you get to the speed of light. We find that the length of an object actually decreases almost infinitely the closer you get to the speed of light. So the first example here, we had someone going at 63% the speed of light. Same kind of canceling out happens. 63% speed of light squared, the 63 gets squared, and the c gets squared. The c squared over c squared cancels out. It leaves us with 0.63 squared, subtracted from 1, and we get 0.6031. If we square root that and times by 100, I know this doesn't look fairly normal, but it's 78 meters. I had it to 3 decimal places, but we only really are justified in using 2 here. We are given 3 for the original, and we're given the speed to 2 sig figs. So 2 sig figs, our answer seems pretty reasonable. Again, try these before you check the video, please. So hopefully this is just an answer to what you've been working on. What happens when we're going 86.6%? We have a little bit more sig figs there, so we're entitled to a bit more. But when we replace velocity with 0.866c and c squareds cancel out, 0.866 gets squared, gets subtracted from 1, and we get 0.25. We square root that and multiply by 100, and we get 50 meters, exactly half. So we're not even getting, yes, we're going fast, but we're definitely not close to the speed of light yet. Now we are. We're only 0.001 away from the speed of light, percentage points away. What kind of effects that going to have? Well, we've seen it already get a bit smaller from 78 to 50, and we're kicking it up a notch. This will not be a linear function. as far as what the results are, they get much smaller, much quicker as we go along. So we square 0.999, we subtract it from 1, and we get a very small number. Now when we square root that, the number gets slightly bigger. It's a bigger fraction. But still, when we multiply by 100, and we end up with a very small 4.5 meters. And this actually leads to one of the problems. This is not in the text. One of the problems I remember from physics, not only is there time dilation, it gets bigger, there's a shrinkage of our length, there's also going to be an increase in the mass. I won't bother explaining how that works, but think about it this way. If we have a spaceship and we want to be able to reach other galaxies, we want to go at the speed of light or faster, yes, there's going to be some problems with our loved ones back home aging too fast. But how do you find a source of energy to do this? Because if mass is going to become infinitely big and length becomes infinitely small, then you have essentially an infinite density of things that you have to move. In order to move something that has an infinite mass but a very small length, you will need an incredible source of power to be able to move it. Matter of fact, you'd be close to having to get an infinite amount of power to move something that has an infinite amount of mass. One of the reasons why faster than light travel looks good in Star Trek, looks good in Star Wars, not that realistic in real life. So your next lesson, and the last lesson for the section, will be on some of Einstein's other findings, including the relationship between this factor 1 minus v squared over c squared, and how that actually works into one of his more famous equations, that energy equals mass times the speed of light squared. The energy and mass are in fact related, and they're related by a big number, because if you have 300,000 kilometers per second for the speed of light and we square it, it's going to get really big. So hopefully we can get through one more lesson and finish chapter 8. And we're getting closer and closer to being done, folks. Hang in there, keep the faith, and have a great day.